I want to look at today, this is kind of a honors topic. We're just going to look at some applications of rational equations. So what are some things we might need this stuff for? So what about something like this? Maybe we've got some kind of a formula where we're talking about resistances or something like that, where R maybe stands for resistance, and that's what this would probably come from. And then this is resistance through one path in a circuit. That's the resistance through another path if they're in parallel, and we're trying to find the resistance of the circuit. So what if we wanted to solve for R1 for whatever reason, right? What would we do? And it's not, okay, so today, it's not like there's going to be a one size fits all today. This is just, every problem is going to be a little bit different, but they all rely on the algebra that we've been studying. So what would our approach be in a situation like this? What do you think? So we want to isolate R1. What might be some steps? Right now it's difficult to isolate though, right? Everybody agree? Because it's in the bottom of a fraction. So what do you think? What are some things we could do? Just throw out some ideas here. What are some things we could do? Say it again. Okay. How would we do that? Fractions make things inconvenient, don't they?
Yeah.
Right. We've been dealing with this all year. When we way back when we were adding and subtracting expressions that involved fractions, we didn't have any variables on the bottom at the beginning of the year, but we still found it convenient to clear the fractions first, right? To get rid of all the fractions so that the equation looked more manageable without fractions. What do you think? How could we do this? Ideas. Getting that R sub 1 out of the denominator is probably a good idea. How have we been solving rational equations? Equations involving rational expressions. What have we been doing? What's our strategy? What do we always try to do first? Okay, how come? Yeah, we want to find the LCD, and what do we do with it? Yeah, we distribute it through, right, to clear all the fractions. Okay, so why not? Why not do that now? So the first step would be clear the fractions by multiplying all, distributing both sides through by the LCD, which would be what? I mean, what's the least common denominator here? Well, I've got pretty simple factors in the denominators, right? They're not polynomials, they're just monomials. And we know that the LCD is the product of all the factors that show up in the denominators. So wouldn't everybody agree that's my LCD? R times R1 times R2. Any thoughts? Does that make sense? Okay. Those are all the factors that show up in the denominators. So if I distribute that through, what am I going to get for the first term over here? If I distribute, I'm really just doing this, right? I'm just going to distribute that to each term. What do I get for the first term?
R1, R squared.
R1, R2, right? Because the R's would cancel. Good. So we get that, right? We get R1, R2 on that side. What are we going to get? What are we going to get here?
R2.
R2, and here we get R1. Okay, so like that, right? Okay, now what? So we're trying to solve for R1. Okay, now we've got an equation with no fractions, but I've got R1s. If we go back to this last step, look, I've got R1s there and there. So how am I gonna? I can't isolate yet, can I? Right? If we go back and we think about this in terms of order of operations, remember what we said at the beginning of the year. When we can point to a single variable, then we can isolate it with inverse operations, but we can't do that yet, right? So what are we going to do to get to a point where we have a single R1 that I can isolate? Divide out the R2. We might eventually get there. If I just divide everything by R2 now, it's going to go away from those two. but I'm gonna end up with this last term is gonna be R1 divided by R2, right? And that's not really solving the problem yet. So you gotta think ahead a little bit here. How could I possibly get a single term with an R1 in it? What if I had a similar problem? You would know exactly what to do. What could I do? Okay, we're going to, right? What would happen if we had something like this? What if I had 2x minus 3 equals 5x? What would you do?
Move the 2x to the
Okay, yeah, you'd push the 2x over here, wouldn't you? Right? Does that make sense? Okay, I could even do that. What if this were something like, what if I had multiple variables? Like, what if I had, let's change this a little bit. What if I had something like a y there and I want to solve for x? Wouldn't I do the same thing? Push the x terms all to one side, right? Does that make sense? I'm still going to do that. So push all the terms with the R1. So those two terms need to be on one side. So we could just subtract that term over to that side. Okay, now let's keep track of our variable that we're trying to isolate. There it is. Now what? What can I do? Combine like terms. I mean, what do you mean by that? Because I can't do much more than that. But maybe you might be thinking the right thing here. What do you mean by combine like terms? How am I going to get an R1 out of that side? Somehow, algebraically, I've got to get an R1 by itself on the left side that I could isolate. How can I go from this expression where I've got an R1 in both of those two terms to an expression on the left side where I've only got a single R1 that I can point to so I can isolate it? I could factor it out, couldn't I? Everybody see that? Look, I've got these two terms. How many factors are in that first term? Show me with your fingers. How many factors are in that term? Yeah, 2, right? R1 times R2. Two things are being multiplied. Factors are just the things that are being multiplied, right? How many factors are in the second term? 2. R times R1. Okay, are there any common factors in those two terms? R1. So why not factor out or undistribute an R1? Okay, that's looking better, right? So now by gathering all the terms that had a factor of R1 in them onto one side of the equation and pushing everything else to the other side, well, it was already there, right? But I want to get rid of all the other stuff. I only want to end up having terms with an R1 on the left side of my equation so that I'm able to factor out an R1. Everybody get that? Then by factoring that out, now look, now we can point to a single R1. There it is, so I can isolate it. What's the only thing I have to do to isolate that R1? Divide by, by that factor. Good, R2 minus R1, okay? And there it is. Okay, we did it. We solved for R1 in terms of the other stuff. I mean, it's kind of an ugly looking expression, but it is what it is. That's it, right? R1 in terms of the other resistances, or R, whatever we assume that's what they are. R and R2, that's what we get for our answer. Okay, give me thumbs. Does that make sense? Okay, so there's one thing that we need to be able to do. We do a lot of this kind of stuff in calculus. A lot of this stuff. You're gonna get tons of practice in calculus with this. But that's something, where now we know how to deal with more complicated looking equations like this, where I'm solving for a variable where I've got fractions involved. Clear the fractions to get rid of them, and then do normal algebra to isolate the variable. Okay. All right, how about something like this? if a 170-pound person weighs approximately 65 pounds on Mars, how much does a 9,000-pound satellite weigh on Mars? How could we set that up? And again, it's not like, don't have an expectation you're going to come out of here being able, I'm going to give you a recipe for solving every possible application that involves rational expression. That's not the point. The point is just to practice, like finding ways to deal with this. What do you think?
Wouldn't it be 65 over 170 times 9,000?
Okay, yeah, so we could set up a ratio, couldn't we? Right? This is a proportionality. We'll spend a little more time at the very end of this unit talking about proportionalities, about different kinds of variation. And this stuff will come up again. But now you've probably seen stuff like this before, right? We could set up a proportionality here where we could say something like, okay, if we take the ratio of the two weights on Earth would have to be the same as the ratio of the two weights on Mars, wouldn't it? So if the ratio of the weight of the person to the satellite on Earth, if the person is 170 pounds and the satellite is 9,000 pounds, even though those values are going to be changed because gravity is different on Mars, the ratio should be the same, right? So we could set up the ratio 170 over 9,000 equals 65 over x, where x is the unknown. That's the weight of the satellite on Mars. And when we get a proportion, we love proportions because they're the easiest equations to solve. What do we do with a proportion where I have a single fraction equal to a single fraction? Cross multiply, right? Cross multiply and you got it. It's no big deal. So we get something like this, right? We would take the cross product 170 times x, there it is, equals the cross product 9,000 times 65, which is right there. And that gives us a really simple equation to solve. Now it's easy to isolate x, right? I just divide both sides by 170 and I got it. So that was an easy one, no big deal. So it's roughly 3,441 pounds. Okay, no big deal. All right. Sometimes though, we get situations where it might be a little tougher, where there may not be just a simple proportion we can set up. Okay, so what about something like this? An experienced roofer can roof a house in 26 hours. A beginner needs 39 hours to do the same job. How long will it take if the two roofers work together? So this seems like a kind of a weird question out of the blue, but this is a fairly common thing that we do in math, is try to look at situations like this where we know we can take this information and come up with the rate at which an experienced roofer gets the job done. We can come up with the rate at which an inexperienced person gets the job done. And now what if we combine forces? What if they're working simultaneously? How does that impact the rate at which they work? Okay. So what are some things we can do? Well, always when we're looking at an application, the first thing is make sure you understand the problem. And we've gone through, this is just a general guideline. Anytime you're looking at an application, these are some good steps to follow if it's a challenging one. Read and reread the problem. Okay, so what are the things that we need to do here? Well, we're trying to figure out how long it's going to take both of them working together. I'll look at two ways of doing this. This is the way that the kind of our textbook suggests, and it's fine. There's another way you can look at this that might be, I don't know, you can decide whichever way seems mentally to match the way you think about this. It's fine. The multiple models work. By using the times for each roofer to complete a job alone, we can figure out their corresponding work rates in portions of the job done per hour, right? So let's set up a variable. Let's let T be the time in hours to complete the job. So then T is going to be the number of hours per roof, right? For the experienced roofer, how many hours are required per roof? 26, right? For the inexperienced roofer, 39 hours are required per roof, okay? So the hours to complete the job would be 39 and 26. Now, if we want to turn this into a rate, well, we could flip this around. We could ask ourselves, what portion of the roof is being finished per hour, right? If it takes an experienced roofer 26 hours per roof, how many roofs per hour is that guy doing? Is he able to? 1/26th, right? He can't finish a complete roof, but he can get 1/26th of a roof done per hour. Does that make sense? So the reciprocal of this number, the reciprocal of T is always going to give us a rate. Like if we know a time it takes to do something, the reciprocal is telling us, well, what percentage of that thing are we getting done per hour? Give me thumbs on that. Does that make sense? Okay. Any questions on that? Can you ask a question to clarify if you're not feeling 100% on that one? What about it seems not quite right? Or maybe you're just not, it just takes a while to get there. If you think of one, raise your hand. Questions are great. So this is the rate, like if we attach numbers to this, this would be in, the units of this would be hours per roof, right? What would the units of this be? Yeah, okay. Or roofs, I guess we should say probably, right? Roofs per hour. Okay, makes sense? So together, we could say that the total time that's required for these guys to do this job, we'll just call it T, and we don't know what that is yet. That's what we're trying to find, right? Maybe we'll call this rate up here, like this is T sub E for the time for an experienced roofer, and this is the T sub B. That's the time for a beginning roofer, and we're trying to find the time if they work together, okay? Well, we can't find that directly, but what do you think about the rates? If a beginning roofer works at a rate of 1/39th of a roof per hour, and an experienced roofer works at a rate of 1/26th roofs per hour, what rate do you think they would work at together? Those are kind of complicated numbers, but let's just say if you've got two people who are, what are they doing? Two people are eating hot dogs, and one person can eat 5 hot dogs per minute, and the other person can eat 3 hot dogs per minute. There's 2 rates. How many hot dogs per minute together could they eat? How'd you get that? You added them up. Okay. So what about this one? Let's shift away from eating unhealthy hot dogs, and now we're talking about roofs. If one person can finish 1/39th of a roof per hour, and another person can finish 1/26th of a roof per hour, how could I determine combined what their rate would be? You could add them up, couldn't you? Right? You could add them up. If I convert these things to rates, the point here is that rates are additive typically, right? You can just add rates at which things are being done together. Whereas we can't just add the times together. It doesn't make sense. This would make no sense at all. If it takes 39 hours for a beginning roofer to finish the house and 26 hours for a experienced roofer, obviously we're not going to add those together. If they're working together, it's going to decrease the time, not increase the time, right? But the rates do add. Okay, so then couldn't we come up with something like this? The rate of the 2 roofers working together, I've got 1 over the amount of time for an experienced roofer. That's the rate, right? 1/26th of a roof per hour plus 1/39th of a roof per hour is 1 over, I don't know, right? We don't know what percentage of a roof they're gonna build together, but by adding these up, we can figure it out. Does it make sense that equation has to be true? Especially if you see the units in there, it really helps, right? So this is, we'll call this the rate of the experienced roofer plus the rate of the beginning roofer equals the rate combined, right? What would the units be? So that's 1/26th of a roof per hour plus 1/39th of a roof per hour equals, I don't know, 1 over T of a roof per hour. Solve for T. Well, we can solve that equation. What would I do to solve that equation?
Common denominator and then add. Oh wait, which one?
Okay, you're right. I mean, common denominator, but how do we solve, like, what have we done here? Maybe you guys may not be through this assignment yet, but what do we do to solve rational equations? What's our strategy?
Trying to do a decimal.
Wait.
Not that.
Not that. We'd rather have fractions. But what, there you go. Clear the fractions, right? Clear the fractions, and then solve the equation with the fractions cleared. Make sense? Okay. So that's what we're going to do, right? What is the common denominator? Well, I mean, if we want to come up with a common denominator, it has to be the product of all the factors that show up in any denominator. So we could factor this. 26 factors into what?
13 and 2.
Good. So 26 becomes 2 times 13. 39 factors into,
13.
there you go, 3 times 13. And this is already factored into t. So what's my LCD going to be then? Well, what are the factors that show up in the denominators? Looks like I've got a 2. I've got a 13. Any other factors that show up in denominators? 3. Anything else? T. So what is that? Well, 2 times 13 times 3 is 78. T. Did we have to go through that whole process? I mean, you can, but you guys probably could have told me if you thought about this a little bit. If I asked you, what's the LCD of 26 and 39? You probably could have just come up with 78 by thinking about those numbers too, right? So 78 would be the smallest number that 26 and 39 divide into, and then I'd need to also have a t in there. Okay, give me thumbs on that. Does that make sense, coming up with that LCD? So then if we distribute that, what do we get? Well, 78 t over 26, 78 over 26 simplifies to 3. 78 over 39 simplifies to 2. Now I combine like terms, 5t equals 78, so t equals 78 over 5, which is, if I turn that into a decimal, just so it makes more sense to us in terms of hours, about 15.6 hours. Okay, make sense? Okay. So again, what was, if we kind of think about this in terms of what kicked this thing loose? What was the idea that allowed us to do this problem? The idea was, when we wrote these as rates, the rates were additive, right? The rates of whatever job we're trying to accomplish, roofing houses, if we write those as rates where the time is on the bottom, we can add those things up, okay? All right, let's see, one more. Oh, yeah, here's another way to look at this one, right? Just kind of, I thought this clarified things a little bit. And we already kind of did this stuff, right? If we call R sub E the rate at which the experienced roofer is able to work one roof in 26 hours, so it's 1/26. Beginning rate is 1/39, right? One roof in 39 hours. Then we can combine all that stuff, right? Where if T is the total time, the total rate is one roof per T hours. And we get that equation, right? The roots add up, the rates add up. The total rate would be 1/26 plus 1/39. Okay, we know that those have to add up to 1 over T. And then we just do the same math. Okay, so for your notes, I think this is to me, this is a little clearer way of thinking about it, a little clearer way of expressing it, but you can decide. Okay, what about this? So lazy river's current is 5 miles per hour. A boat travels 20 miles downstream in the same time as traveling 10 miles upstream. How could we find the speed of the boat in still water? Same boat, same engine, whole bit. So what do you think?
It's a tricky one.
That is a little tricky. Okay, what's usually useful is see if we can come up with an equation where we can express these in terms of rates, right? So what is seems like we're talking about distances and times, and our rate would just be speed here, right? When we say rate, everybody agree that means speed in this case? So you guys could all tell me that distance equals rate times time. You've done stuff like that for a long time, right? Distance equals speed times time. Or in other words, if I write that in terms of t is just distance divided by speed, right? If I solve for t. Make sense? Okay. Now what? So how are we going to get the rate? The boat has this certain speed at which it travels in still water. How come it's able to travel 20 miles downstream but only 10 miles upstream? Why can it go so much further downstream?
Is that the current?
Okay, because the current is adding to the speed of the normal speed of the boat, right? If we're traveling upstream, the current is being subtracted from the normal speed of the boat. We're not making as much headway, right? So then does it make sense that we could say something like this? The rate of the boat downstream would be water, the rate of the boat in still water, so the boat's normal speed plus the current. Rate of the boat going upstream would be the normal speed of the boat minus the current speed. So we could summarize it maybe something like that. Okay. If R, we'll call R the rate, that's the speed of the boat, and that's the normal speed of the boat in still water. If the current was 5, then doesn't it mean that our downstream rate would be R plus 5 and upstream would be R minus 5? Everybody agree? Okay. Well, what's the amount of time? It tells us that the time is the same to travel 20 miles upstream and 10 miles downstream. Well, the time we just established up here, time is just distance divided by rate, isn't it? So the time it takes to go downstream would be the distance that we travel, which is 20 miles, divided by the rate, which is R plus 5. Okay, make sense? What about going upstream? Well, again, time is just distance divided by speed, or distance divided by rate, so that would be 10 miles divided by my slower rate of R minus 5. The key here that allows us to do this problem is this statement right here. In the same time, right? So if I come up with expressions for the time going upstream and the time going downstream, because I know they're the same, what could I do to those two times? Set them equal to each other. How many unknowns are there then in that equation? Just one, so we're good, right? If there's only a single unknown in our equation, if we're good enough at algebra, we should be able to isolate that and figure out what it is. So we just come up with an equation where we only have one unknown, one variable, which is R, which is what we're trying to find. Now I've just got to solve that. Well, this ends up being actually a pretty easy one. Setting it up was a little bit tricky, but now that's just a ratio. What do I do with a ratio? Or a proportion? Yeah, just cross multiply, right? Because I've got a single fraction equal to a single fraction, so I can just do this. Let's do, doesn't really matter. Let's do this one first. So 20, I get 20 times the quantity R minus 5 equals this cross product. 10 times the quantity R plus 5. Well, that's pretty easy now. Now what would I do?
Distribute.
Yeah, I just distribute. So that's giving me 20R minus 100 equals
10R plus 50.
10R plus 50. And now this is just elementary. What do I do now? Yeah, good. So I want to push the R's to one side. Right, push them to that side so I have a positive number of R's. While we're at it, where would I want to push all the constants? Other direction. Good. So how many R's do I end up with on the left side?
10.
10? What about the other side?
30.
150? So what's R? 15. There we go. So now we know the speed of the boat in still water, 15. And for your notes, I'll just include this stuff, right?
Is it always gonna be like, is it always gonna end up being like, cause in this case, like 15 is the middle between 20 and 10, is it always gonna be like that?
For a problem like that, I think it will.
So it's like a cheat code, now we just know.
No, it won't.
Dang it.
No, it won't. It won't. It won't. It just so happens because, yeah, it won't always. But the math will still be just as easy.
Yeah.
Okay, so here it is. I'll just uncover all this stuff for your notes, but we just did all this stuff. Okay? Again, you're going to see some other ones that might seem a little different than this, but you get the idea, right? You just got to somehow come up with a way of setting up an equation. What do you think these equations are all going to involve? Probably rational expressions, because that's the unit we're in. But then you're just going to, tackle those using the algebra we've been practicing. Okay? Have at it. I'll quit talking.
You